The main application of a Poisson distribution is in something called the Poisson process. And what the goal is here is you're trying to model the number of occurrences of some rare event that happened in a fixed period. Now, you should be careful when we say the word period here. It might refer to a time, it might refer to a length, could be anything. So generally, for the purpose of kind of introducing the concept to you, we will think of it as time, but it could be anything. Now, in general, rare events don't happen at a uniform time or uniformly spaced. So rare events occur non-uniformly. So let's say that we start the clock here and maybe the first event happens right there. So there's the first occurrence of a rare event, and then some longer time elapses before the next one happens, and then some other time happens before the third one, and let's say we are interested in running the clock from there to there. So the spacing between these events in terms of time is not uniform. Okay? You are typically given an average rate of occurrence. So it could be the number of events per minute, or the number of events per meter, or the number of events per object, whatever it is. It really just depends on the problem you're working on. So the idea with a Poisson process here is that you try to model the number of events using a uniform spacing with the same average rate. And the average rate in here is going to be a lambda, and so we're going to call it lambda. So essentially the picture looks similar. You start the clock there, and you end the clock there, but here you're going to make the spacing the same. So you're just going to make it uniform in a way to come up with a simple model to help you get accurate results. So again, you're not interested in the time between the events or the space between the events or anything of the sort. You're just interested in the number of events. That's the goal here. So when we have a random variable, we're going to say that this is the number of events that occur. And it will turn out that the number of events is going to be modeled by a Poisson problem, but the parameter is going to be lambda times t. So the average rate times the duration. Okay? If you want to think of it, right, this could be the number of events per time, and t has units of time. And so when you multiply the two of them together, the time units will go away. And so this is the idea. If you want to model the number of rare occurrences, the appropriate model to use is going to be a Poisson, but this time the parameter will be the average rate times your total time. Now on the PDF that I've attached, there's a second example where here we're going to be interested in the number of flaws on a boiler. And so you take them from the assembly line and you just check to see how many flaws there are. You've been told that there are 5 flaws per boiler. Now we're interested in the probability that I will get exactly 8 flaws on one boiler. And so the probability here is going to be dependent on the distribution. We can use the mass function here. We are going to have a Poisson distribution, lambda t. So it would be a Poisson distribution of 5 times 1. So 5 flaws per boiler times 1 boiler. So a Poisson distribution where it's 5. So in this particular case, if you wanted to calculate this, you could use d Poisson in R. And if you use d Poisson in R, what you're going to get is, well, you'll use this command, d Poisson 85, 0.06527 with some change. So there's a very low probability, relatively low, 0.065, so in the ballpark of 6.5% of the time. If you were to take boilers off the assembly line at random over and over and over and over and over again, this model says that about 6.5% of the time they should have 8 flaws on them. Now the second question says, okay, well, what happens if we say instead of checking over one boiler, let's check over 2 boilers? In this case, the model, the appropriate model, would be a Poisson distribution, 5 times 2. So it would be a Poisson distribution where we'd use a 10. And so this makes a difference, because now if we go about and we calculate this probability, and we can and we should use some technology like R. We would use d Poisson 8, 10. This turns out to give 0.112599. So about double, much larger. And this makes sense. If I were to say, let's take 2 boilers and check what the chance is of having 8 flaws in total, the chance of 8 flaws over 2 boilers should be higher than the chance of seeing the 8 flaws over 1 boiler. And this makes perfect sense. Okay. And so again, the Poisson process is a way of using the Poisson distribution to model rarely occurring events in some fixed period, whether it's time or length or objects, etc. All you have to do is use a Poisson mass function, but you modify the parameter.